Alright, so we have the set A, and we want to prove that we have a function f defined on A such that both directional derivatives or derivatives with respect to both x and y are 0, then f is constant. So let's see here. So let's start with part A. Let x1 and x1, y1 and x2, y2 be 2 points in A. Then, okay, so before proceeding, let's actually draw this out to get an idea of what this looks like. So this will be R2. We've got the x-axis and the y-axis. And so if x is greater than or equal to 0, then y cannot be 0. So we sort of have this like sliver of points of the form x comma y where x is greater than or equal to 0 and y equals 0. And this line is completely removed from A. So everything... So this sort of thing... Well, I guess that's sort of deceptive to shade it in because it's not... It's not a region with any interior. It's just like we've taken like this line and just removed it. Of course, all this thickness you see here is just a visual representation. But anyways, what A is everything outside of here. Start like here. So let's say that we have two points. Let's say x1, y1 is here, and x2, y2 is here. So what we want to do is, we know that if we have any line in A, if we have any vertical or horizontal line in A, then the function f will be constant on that line. Because if you have a horizontal line, then the only value that's changing is the y input, and d2 of f is 0, so the y input, or the function, does not change when you plug in different y values for a particular fixed x. This sort of goes back to the exercises about if d1 of f is 0, then f is independent of the first variable, and if d2 f is 0, then f is independent of the second variable. So anyways, the idea here is that we choose some number over here. It doesn't matter which one, just some number less than 0. I'll go with -1. And we do this. We sort of make a path from the first point to the second point. And so what you do is you go from x, so if this is x1, y1, and this is x2, y2, then this point up here, this is going to be -1, y1, this is going to be -1, y2. So this is how you get from x1, y1 to x2, y2, and you can do this for any 2 points in A, because this line from -1 to y1 to -1 to y2, that's always going to lie in A, and then when you connect from -1 y1 to x1 y1, then let's see here, the y value here is going to be, well, I guess there's two scenarios. If one of the points is on the x-axis, so you've got y equals 0, then x is going to be less than 0, and so you're going to be somewhere over to the left here, and so this will work. But anyways, I don't want to go on too much of a tangent here. It's pretty straightforward to see that you can always draw these lines and you're never going to cross over A. Because in order to cross over A, or in order to leave A, what would have to happen is this line from -1 y1 to -1 y2 would have to cross over A. And that can't happen because -1 is less than 0. Okay, so call this L1, L2, and L3. Then lines L1 through L3 lie in A. So if we take f of x1, y1, now notice that, okay, so L1 is a horizontal line, and D2F, it's a horizontal line. So they all have the same y value. So the x values are the things that are changing. However, D1F is 0. So the value of f does not change when you change the first coordinate. So if we replace the x1 with -1, you're going to get the same value because the function f is constant along this line, because its derivative with respect to the first variable is 0. And then since its derivative with respect to the second variable is 0, you can replace the y1 with y2. And then finally you can go back and replace the -1 with x2. And by the way, we only know that f has derivatives with respect to x and y both being 0 only on the set A. And so that's why we can't jump straight from x1, y1 to x2, y2. Alright, so that's that. And now we have to find a function, any function such that d2 of f is 0, but f is not independent of the second variable. So what we're going to do here is, if we look at the quadrants of, the standard breaking up the XY plane into 4 quadrants like you do in, I think this is typically like a high school math thing. But basically what we can do is we can let f be constant in each quadrant, give it some value in quadrants 2 and 3, give it some value in quadrant 1, and give it a different value in quadrant 4. And so then what will happen is that if you're at any point in A, then changing the y value slightly, you'll still stay in the quadrant. And so the function won't change, and so d2f will be 0. However, f will not be independent of the second variable because if you choose x greater than 0 and some positive number y, then x comma y will be in Q1 and x comma minus y will be in Q4, and you'll get different values at those different points. And so what's really going on here, and of course we'll talk about this in more detail when I actually write down the proof, but what's really going on here is A is an open set, and so it's an open set, but we were able to separate quadrant 1 from quadrant 4. Okay, so let's do this. Let f of x, y equals 0 if x is less than or equal to 0. F of x, y will be 1 if x is greater than 0. If both x and y are greater than 0. And f of x, y will be minus 1 if x is greater than 0, but y is negative, less than 0. So for any x, y in A, let's see here. So A is open. And why is A open? A is open because you can choose any point in A and get a neighborhood around it which is entirely in A. And the way you choose this neighborhood is that if If you have a point in quadrants 2 or 3, then you just choose a box, an open neighborhood, whose radius is less than the distance to the origin. And then you're guaranteed to not intersect the complement of A. And then if you're in quadrants 1 or 4, you have to choose the radius small enough so that the y values of your rectangle don't meet that line, that ray of points where y is 0 and x is greater than or equal to 0. And so to avoid that, for whatever y coordinate you have of your point, you make sure that the radius, or that the length of the rectangle in the y direction is less than the distance to that ray divided by, say, 2. Alright, so with that you can see that A is open. And so, if you take any x, y in A, then there is an interval I which contains y such that if you take the singleton point x and take its direct product with this interval I, this will be entirely contained in A. In fact, I don't think we necessarily even need to use the fact that A is open because, well, I guess in proving that A is open, you prove that you can choose an appropriate neighborhood. And that strategy that I discussed for choosing that neighborhood, where you take the distance to that ray of points where x is greater than or equal to 0 and y is 0, and take that distance and divide it by 2 and use that as the radius of your interval with respect to the y direction. That's all that we need here. So all we need is really like one small part of the proof that A is open in this proof. So that would be the more concise way of doing it. But it is true that A is open, and that really is sort of the key to why we're able to do this. Yeah. So this is in A, and F is constant on x cross I. And why is that? That's because, so the x value isn't changing, so all you have to consider is what values could f take on when you plug in different values from this interval I. And if x is less than 0, then it doesn't matter, because while I could either lie in Q2 or it could lie in Q3 or it could intersect both of them, f is constant on both of them. F is 0 on both of them, so it doesn't matter. However, if x is greater than or equal to 0, then I is either going to lie entirely in Q. Well, the point x direct product with I will lie either entirely in Q1 or entirely in Q4, and in either case, it's going to be constant. Okay? So f is constant on this. So that means that the derivative with respect to the second coordinate of f at xy equals 0. Well, no, but the derivative with respect to y of f at x comma y is 0, and this holds for all x comma y in A, and therefore d2f equals 0. Alright. But if x is greater than 0, well, greater than or equal to 0, if we take f of x comma 1, that's going to be 1, and that's not minus 1. And minus 1 is f of x comma minus 1. So f is what? Not independent of the second variable. It's not independent of y. And so there you go. Alright, so that's all that we need to prove here. And I guess the idea is that you can have a function just because the derivative with respect to a particular variable is 0, you're able to make this function not independent of that variable if you sort of create these jumps. So you need to have this, you need to be able to separate quadrants 1 from quadrant 4, and you need to allow the function to jump between there. And then what will happen is that the function will be differentiable on each of those, at each of those points, in each of those regions, Q1 and Q4, but the value of the function can still change because you have this jump. And so this actually is really important when you get to Lebesgue integration, because what Lebesgue integration is based on is constructing functions out of... so you see this function f that we have here. It's got this is, by the way, we're done with the exercise. This is all a tangent. But you could write f as so f is 1 on Q2 or Q3. It's 0 there. It's 1 on Q1, and it's -1 on Q4. Of course, you have to go through and deal with the the set of points where x is greater than or equal to 0 and y equals 0. You have to go through and figure out. You have to make sure that when you define Q1, Q2, Q3, Q4, that you're not including that because f is not defined there. But anyways, so we have this function f, and so we take the domain of f and break it up into a finite number of sets. And on each of those sets, f is a constant value. Such a function is called a simple function. And with Lebesgue integration, what you have to do is you have to try to construct the functions that you're able to integrate with respect to Lebesgue integration end up being those which can be constructed from simple functions. And so functions like f here are really useful it's useful to understand them for later down the line when you learn about Lebesgue integration. And so yeah, it's nice to be able to sort of, I guess it's not absolutely necessary to introduce step functions for this problem, but it gives us a nice way to start thinking about them. But yeah, that's about all there is for this exercise, and we're done.